Hello, so today I'm going to explain inclined planes, specifically the banked curves. So the banked incline on which a car drives around a racetrack, and I'm going to explain later on how to solve, friction problems associated with this type of situation. So what happens? Why do we draw the components in a different way from the inclined plane? Well, I'm going to explain right now. So in the inclined plane, let's say the one you would usually see previously, I'm just going to label it. We have the inclined plane. It's just going to be this incline. And if you haven't watched my video on inclined planes, please do, because I do explain it more thoroughly there. But we have this mass on top. It has a mass of m. And it gets pulled down by gravity, giving it a weight of mg. And there's a force normal by the surface on it, perpendicular to the surface, which is F of n. So the force normal, remember, it's always when it's the force that this surface, any surface, has on the object as a reaction to the object's force on the surface. And it's always perpendicular to the surface. So in the case of inclined planes, the only force that's actually being applied to the object, well, let's say, except for the normal force, is the force of gravity. And that's why the object will slide down this plane, because the force normal, unlike on a flat plane, so for example, if we were to draw a flat plane, we would have this object right here, m, it would get pulled down by mg, and the force normal would be up on the object. In the case of a flat plane, the force normal can directly oppose mg, and therefore the object remains at rest. It does not fall down. The force normal is equal to force of gravity. But in the case of an inclined plane, this force normal is going to be smaller than the force of gravity. That's why the object will slide down. The force normal is not enough to maintain the object in its still position. So that's why the object slides down. And that is also why the force normal, since it is less than gravity, and it's, caused by gravity technically, because if there was no, gravity, there'd be no force normal in this case. The object wouldn't be exerting its weight downwards. So because force normal is less, force normal in this case is a component of gravity. So I explained this previously, but we're going to draw it right here. What happens is that the force normal is just a component. So there's this angle right here, theta. So it's right here, theta. And the force normal will equal to mg cosine of theta, which is apparent in this case, because it is not greater than gravity. Gravity is the only, force that's causing this normal force. So therefore, in order to find the normal force, we're going to take mg cosine theta and get the normal force. I explained how that's found, how this originates in my previous video. Now, in the banked curve, what happens is different. So let's just label it right here. Banked. My handwriting is not the best today. Banked curve. So what happens here is that we have the incline. So again, I'm going to draw the incline, but things get a little bit more different. So we have this mass again, and in this case, usually in the problems, it would be some car going around, a circle that has these, tilted inclines on the side, like at a NASCAR racetrack, something like that. And again, we have, as usual, we're still on Earth, mg is always downwards. Mg is downwards. That's the weight of the car. And of course, there's the force normal, which is always perpendicular to the surface. So that's because the force that the surface exerts on the mass, that's going to be the first force normal. It's going to be perpendicular to the surface. That's always the case. But in this case, instead of like in the inclined plane where the mass slides down, the mass in this case does not slide down. Because imagine if the NASCAR cars just start sliding their wheels against and going down, it'd be a disaster. So this object in this case does not slide on the incline. And what that means is that the force normal in this case has a vertical component that is actually directly opposing the force of gravity. The force normal in this case is going to be greater than the force of gravity because it can now finally fully oppose this downwards motion of m. Just like, let's say, in the flat plane. Except we see that the force normal is tilted. So, to find the vertical component of the force normal, we're just going to do this. I'm going to draw it right here. I'm going to draw it right here. So, it's going to be up like this. That's the vertical component of force normal. And this angle right here, between these two, is actually equal to this angle right here. So that's theta. And that's theta also. And what that means is that f of n, to obtain this part of it, says f of n is going to be the hypotenuse in this triangle, because the vertical is a component of this f of n. That means f of n cosine theta is going to be the vertical component of f of n. So I'm going to draw it right here. F of n cosine theta. And f of n cosine theta is going to be equal to mg. That's because this object is not moving. Therefore, the vertical forces cancel out. Unlike, let's say, in the previous example with this inclined plane where the object starts sliding down because the force normal is no longer sufficient, to oppose the mg below. In this case, the force normal is it's sufficient because its vertical component cancels out with mg. So f of n cosine theta equals mg. This object remains at rest and does not shift, vertically. That means it would slide down. So it remains at rest, and we'll just write right here that f of n cosine theta equals to mg. And why is all of a sudden this force of normal sufficient to keep this object up? Why does it have these, components? Well, that's because now we have this new component. It is called centripetal force. And centripetal force, we all know that it's equal to mv squared over r. And let's say in this frictionless example, what happens is that the f of n, it also has another component. Since it has an fn cosine theta, it also has an interesting component right here. I'm going to draw it right here. There it is. That is going to be this component right here. That's going to be f of n sine theta, because remember it's opposite to the angle. So f of n sine theta is this horizontal component. And remember that the object, while it's going around this curve, it has this inertial tendency to escape this curve. While it's moving fast enough, it has an inertial tendency. And that's why, to make the object still, this horizontal inertial tendency of the object must be opposed by the centripetal force, which is equal to mv squared over r. And mv squared over r in this case, the only thing that's actually exerting this force in this case is f of n sine theta. So f of n sine theta in this case must equal mv squared over r to keep the object from sliding down, because otherwise the object would have its inertial tendency and it would escape this curve, but instead it keeps circling and does not slide because the f of n sine theta exerts a force that is equal to mv squared over r. It exerts the centripetal force, and therefore it prevents the object from sliding. So I'm going to draw it right here. Mv squared over r in a frictionless example is equal to f of n sine theta. Well, now that we have the components of the f of n in a banked curve, how do we exactly figure out what happens when there's friction? Well, when there's friction, we do something different. So when there's friction, I'm just going to move it right here. I'm going to draw this banked curve again. And things get a little more complicated. So let's say we have this mass again. Mass. Right here. And again, it has the force normal, perpendicular. And it also has this thing. So it also has the weight of the object, which is going to be vertical, mg. Again, we have our theta right here. Again, we have the components of f of n. So f of n has this horizontal component, which is going to be f of n sine theta. It has its vertical component, which is going to be f of n cosine theta. But where exactly does the friction come in? Well, it depends. Let's say that this object is moving really fast, like very fast. It's moving so fast that the f of n sine theta, let's say f of n sine theta is no longer equal to mv squared over r. It's no longer enough to oppose mv squared over r. So it's no longer providing the centripetal force of mv squared over r that's necessary to keep the object from sliding up. And now the inertial tendency of the object, there's not some force that's causing it to slide up, it's just an inertial tendency to escape. Now the object slides up because f of n sine theta is less than mv squared over r in certain situations. Well, what does that mean? That means that there is a friction that's going to be going against this sliding out. So if the object is sliding out, the friction is going to go the opposite direction. So in that case, when the object's going too fast, I'm just going to draw the friction component. So the friction is going to go down the plane, just downwards. Let's say it's going to be called FR. FR for friction. And I'm actually going to draw a separate diagram just to show it a bit more clearly. So just draw right here. Theta. And what happens? Let's see. So M is right here. And we have this friction force. It's going this way because it's opposing the motion of M outwards. So FR. And this is the horizontal, just the regular horizontal. Remember, since friction is a force, we must find its components. So it's going to have certain components. Friction is going to be a hypotenuse in this case, so FR. And so, interestingly enough, this angle right here is going to be equal to theta again. Because why? It's because you notice this line right here and this line right here. So this one right here and this one right here, they're parallel. And this right here is like a single line almost. So if you've ever taken geometry before, or you can imagine even, this angle theta is going to be equal to this one. So not that difficult. But here's the difficult part. So f of r, in this case, there are two components. There's f of r cosine theta. There's f of r sine theta. And that's cool because we see that f of r sine theta is going to be opposite of this angle. F of r cosine theta is going to be adjacent. Well, that's cool, but that doesn't tell us exactly what's going on or how to solve problems. So in order to find, let's say, the maximum velocity of the object on a banked curve, first, obviously, we have to know the angle theta of the curve. And once we know that angle, things become a little easier. So once we figure out theta, which is usually given in the problems through some clue, then what happens is that if the velocity is this big, now that the f of n sine theta cannot fully generate mv squared over r, this friction, so remember, f of n sine theta, when the object's moving too fast, it's not enough to generate this mv squared over r. The mv squared over r is going to be greater than f of n sine theta, and the centripetal force will not be able to resist the object's, horizontal inertial tendency. So this frictional force, that's where it comes in. The f of r cosine theta, this horizontal force, will help the f of n sine theta to generate a force of mv squared over r that will prevent the object from sliding outward. And in this case, we're talking about horizontally, so if it's sliding outward, you would imagine the object is relatively also moving horizontally. So, this is the formula that results. Look at this. F of r cosine theta plus f of n sine theta. Now, I'm drawing parentheses around some of these thetas. Some don't have parentheses. It doesn't matter, just as long as you get it. Equals mv squared over r. So now these two, the friction that's opposing the object from sliding outwards, and the f of n sine theta that's also opposing the slide outwards by going this way, the object sliding this way, they will finally generate a force that is equal to mv squared over r, which will be able to prevent the object from flying out the plane. And also, often this equation is not enough to solve the problem. We can generate a second equation. So if the object is sliding outward, it's not just moving relatively horizontally, it's also moving relatively vertically because it's sliding upward. So if the f of n, so now the mg is not enough to oppose the f of n cosine theta. The f of n cosine theta becomes too big for mg to oppose because we have, this object's tendency to go upwards. The f of n cosine theta will, if mg just remained, the f of n cosine theta would be greater and the object would slide outwards, but not with this friction. The vertical component of the friction, f of r sine theta, combined with the force of gravity, mg, now can directly oppose f of n cosine theta and therefore keep the object relatively still vertically. So the object doesn't move anywhere vertically, therefore doesn't move up. So this is the resulting equation. mg, so that's the force of gravity downwards, plus f of r cosine sine theta equals f of n cosine theta. If they are in fact equal, the sum of mg and f of r sine theta, which are downwards forces, one exerted by friction, one exerted by gravity, and it opposes the normal force upward, f of n cosine theta, the object obviously doesn't move anywhere. It just remains in the same spot on the plane. Just the same way, it doesn't move horizontally. F of r cosine theta, horizontal friction, plus the horizontal component of f of n sine theta equals the mv squared over r, which is the force necessary to keep the object from sliding horizontally. It's a centripetal force. So now if you solve these two equations, you will get the answer. But what does f of r actually equal? Well, f of r, since we're talking about a case where the object is not moving up or down, it's static friction. And static friction, we have learned, is equal to f of n times the coefficient of static friction. You just sub it in for f of r in this equation. Then my recommendation would be to solve for a certain part of the equation. For example, you can solve for f of n in the equation and just plug it into the other equation. There are many ways to solve this, and if you have the angle, it becomes much easier. If you have the angle right here, theta, it becomes much easier. Also, another problem that people have is, how do you find this angle? Well, for example, if a problem tells you that, let's say in a frictionless situation, when there's no friction, that the object can go a certain velocity, then we plug it into mv squared over r. That'll give us the horizontal force that this object is exerting on the plane. And that horizontal force will be equal to f of n sine theta, which is normal force, the horizontal component of the normal force that opposes it. And obviously you can't just solve it from there, because what is the normal force? Well, the normal force, remember, it's also the vertical component of the normal force is equal to mg, since this object is not sliding vertically in any direction. Therefore, f of n cosine theta equals mg, and you can solve for the theta if you know, for example, the object's mass, or even if you don't, you can still, there are ways of canceling out the mass if you solve these two equations together. Now finally, I'd like to explain what happens if the object is moving too slow. This is where things get even harder. So, if the object is moving too slow, again, we have our inclined, the banked curve. We have this m, but in the situation where it's moving too slow, this is what happens. The force of friction is now going the opposite direction. And why is that the case? Well, this is the case because if this object's moving too slow, keep in mind that it is no longer having a, let's say, sufficient, tendency to escape, because the mv squared over r necessary to keep it in is now lower. That means the object has a lower inertial tendency to escape. That means the object starts sliding downwards. And if the object starts sliding downwards, the force of friction opposes it, because the object is just moving too slow. But, it's kind of inconvenient to draw the diagram with the force of friction now on the opposite side of the object rather than downwards. Instead, we can just draw it like this. Watch. We can draw the force of friction like this. But now it's just pointing a different direction, unlike in here where it's pointing downwards. It's pointing, in this case, upwards. And we can draw the same thing. So we can draw this horizontal component. We can draw this vertical component. So this force of friction is going to be f of r, and I already showed it right here. So the horizontal component is going to face this way. That's going to be f of r cosine theta. This is theta. They're the same magnitude, they're just the opposite direction. And this one right here is f of r sine theta. And now what happens is that because mv squared over r, which is the centripetal force inwards, there's only one force that's going inwards, but it's also mv squared over r can also represent the object's inertial tendency to escape this curve. It's not going to be sufficient to oppose f of n sine theta, which points in this direction. So f of n sine theta now is going to be greater than mv squared over r. And the only thing that can be added to mv squared over r, which is the object's tendency to escape, is force of friction. So what happens is that the following happens. So f of n sine theta equals now to mv squared over r plus fr cosine theta. And I'm going to explain exactly what this means. So f of n sine theta is this object's horizontal tendency inwards. It's this, not tendency, it's the force exerted by the plane inwards. And since mv, it's now, since the mv squared over r, the centripetal force of the object is now lower, and that means that the object's tendency to move, outwards, to like move horizontally in this direction, which is also equal to mv squared over r, it's lower. Remember, that's not a force. If we're talking about the inertial tendency, that's not a force. You need a force of mv squared over r to oppose it, but we can also measure this inertial tendency as mv squared over r, just for the sake of this explanation. So mv squared over r, in this case, is not going to be sufficient because the object is moving slower. It's not going to be sufficient to oppose f of n sine theta, which is going in this direction. So it's going this way, downwards. So in this horizontal direction. So f of n sine theta would be going this way. And the object's inertial tendency, not a force, inertial tendency, we can measure its magnitude as mv squared over r, and that would be going this way, the opposite way. But mv squared over r, because the object's moving slowly, it's not enough now to oppose the f of n sine theta this direction. So what happens is that unless something else is added on to help mv squared over r to oppose f of n sine theta, the object is going to slide down. So in this case, the force of friction comes in handy, because the force of friction now, it is going this way, opposing the object's motion downwards, and therefore opposing f of n sine theta. So the horizontal component of the force of friction is going to oppose the horizontal f of n sine theta. So what is the horizontal component of friction? It's going to be f of r cos theta, which in this case is pointing opposite to f of n sine theta. So we can see f of r cosine theta plus mv squared over r, these two, mv squared over r in this case is an inertial tendency, and f of r cos theta in this case is a force. They oppose f of n sine theta, and therefore when they're equal, the sum of mv squared over r plus f of r cos theta is equal to f of n sine theta. The object does not move anywhere horizontally and therefore does not slide anywhere, because remember, I explained before that if it's moving horizontally, it's technically sliding in some direction. It's just relatively moving horizontally. And what about vertically? Well, vertically what happens now is that, f of n cosine theta So in this equation, what happens is that the f of n cosine theta, which is the vertical component, and it's pointing up, and the f of r sine theta, which is also a vertical component, as we can see right here, it's equal to mg. Because mg in this case, since remember the object is moving slowly, it would probably start sliding down. Therefore, mg is the enemy here because mg is in favor of it sliding down. And f of r, in this case, is against it sliding down. Therefore, its vertical component will oppose it sliding down, f of r sine theta. And f of n cosine theta, in this case, will actually oppose the slide down. So f of n cosine theta, in this case, will also be a vertical component up, as usual, because this plane exerts a component that's the force of normal that has a vertical component upward. So these two, when they're equal to these forces upward, when they're equal to this force downward, the object does not move anywhere vertically. We're not incorporating mv squared over r in this case because mv squared over r is a horizontal force. It's a centripetal force, horizontal. In this case, we're only talking about vertical forces, and this is what happens vertically. And now we have this the system of two equations, just like we had before when the object's moving too fast. And again, we can use it to find the v and find, therefore, the minimum velocity with which the object can travel on the plane without sliding down. And f of r in this case will also equal to f of n times the coefficient of static friction. And that is how you solve these friction problems, and that's how you understand banked curves. These equations can get a little complicated. Try not to get confused. All the angles you'll probably be dealing with are angle theta. Keep that in mind. Keep in mind that force of friction has two components, f of r cosine theta, f of r sine theta. Force of normal has two components, f of n cosine theta, f of n sine theta. And keep in mind who's vertical, who's horizontal. Keep in mind that there's mg. Keep in mind where the force of friction faces. If we're sliding up, force of friction is going to face the opposite direction down. If we're sliding down, force of friction is going to face the opposite direction up. Keep that in mind, and I hope that this video can help you solve some problems.